Hey you guys, welcome back to the channel PHYSICSSIRJEE, and here we are in Resolved series, and I've brought forward to you a problem on rotational and irrotational flows and also the concept of Bernoulli's equation, whether it is applicable for 2 points on two different streamlines. This is something that generally bugs a lot of students, toppers included, and so here we are going to resolve this issue. Not only we are going to resolve this issue through a problem, but also I'm going to give you 7 practice problems at the end of the video and their solutions in the later stages in order to ensure that we have a complete post-mortem of this particular concept at JEE advanced level. Also, some bonus information and sources in this particular video for the physics Olympiad enthusiasts as we move along. So, lot of excitement to follow. So I hope you stay invested in this particular video till the end, and also make sure that you do have a notes and a pen to take down the things as you go along with this video, especially if you're a serious aspirant. Okay, so here we move on to the problem statement. As we do with any resolved series, we'll take up a physical situation and start decoding that situation by ensuring that we go into deeper aspects of the problem. Okay, so if you want to give it a try, I've already shared this in the community post. So in case you missed it there, pause the video here, try this one out for maybe 5 minutes and do come back for the complete explanation, and also a lot of concepts being explained before I take up the solution of this. Okay, so here's the formal wording of the question. A flat closed tube of uniform cross section has an inner radius A and outer radius B. It is filled completely with water and is kept flat on a horizontal surface. Now, entire water in the tube is rotated with a uniform and steady angular velocity omega about the vertical axis of the tube. Okay, so what you're looking at in this particular picture is the top view of this tube. Viscous forces between the tube and water are neglected, and the density of water given is rho. 1 and 2 are 2 points in water. 2 is very close to the inner surface, and 1 is the one which is almost at the outer surface inside water, as shown in the figure. Let P be the pressure and E be the energy of the fluid per unit volume. If nothing is mentioned, this energy is the mechanical energy, which contains the 3 forms of mechanical energy in Bernoulli's equation. Then, which of the following 4 options, one or more than one may be correct, is the most appropriate based on the information given? Okay, so I hope you have given it a fair try by pausing the video. I'm moving ahead with the pressure calculation first. So 2 options are related to the pressure difference between 1 and 2, and the 2 options are related to the energy at 1 and 2 per unit volume. Okay, so let's move forward. Solving for the pressure difference is the slightly easier one between the two concepts. So if I take a fluid element, a lot of things on the board, as I keep saying, just follow my lead, try to look at where I am pointing on the board, listen carefully to what I am explaining, then you'll all be all right. Okay, so here we go. First to the figure. Do you see a fluid element here of radial width dr and into the page area of cross section dA? The dA is not visible to you right now, on which this pressure and P plus dP pressure act. Okay, so we could say that the volume of this small cuboid element is dA into dr. Okay, right. So this particular dm element is actually going in a uniform circular motion depicted by this blue circle. Okay, and this green circles depict the solid container which is at rest. So at any arbitrary distance small r, for the uniform circular motion of the dm element of radius small r, the inward force, this is horizontal force, inward horizontal force is due to this excess pressure, dP multiplied by the dA that I already spoke of, the area that you don't see into the board, should be equal to the provider of the centripetal acceleration, okay, into the center. Okay, so mass into the centripetal acceleration is r omega square. So if you write dm as density into volume by writing dA into dr, dA can be cancelled on both sides. You get a differential value of the pressure dP as proportional to r into dr. Since omega is uniform in the question, that means what is meant by steady? Steady means something that doesn't vary with time. What is meant by uniform? Uniform means it doesn't vary with space. That means spatially speaking, that means every point has the same omega. Somehow you have maintained the liquid to be moving with same omega about the center. Okay, so when you are integrating on both sides, the omega square and rho both come out. it need not be always true. Because the given condition talked about omega being uniform, you're able to bring it out of a space integration. So RdR integration is a pretty simple one. And when you substitute R1 and R2 as the limits, which are given as A and B, then you end up getting P1 minus P2. And it's quite obvious that due to this entire rotation, the liquid pushes the wall at 1 more than at 2. It's quite predictable. So P1 minus P2 is a positive number, and upon integration gives you this expression, which is one of the options. We'll go back and mark that. But when you notice something very clear here, since you got P1 is already greater than P2, according to this, you also know for same omega at 1 and 2, since 1 is at a larger distance, you realize the velocity of fluid element at 1 is more than 2, which is slightly concerning for students who would have thought that Bernoulli's equation is applicable between 1 and 2. Remember, this is all horizontal diagram, therefore there is no gravity effects. So the value of the energy per unit volume, E, is in this problem given by pressure energy and the kinetic energy per unit volume, which is half rho v square. So if P is more for 1, and V is also more for 1, then E1 is not equal to E2. That means you cannot apply visibly the Bernoulli's equation between points 1 and 2. The reason is very clear here, that 2 streamline is different from 1 streamline. But there are many problems in some of our JEE syllabus where we practice problems in which we do apply Bernoulli's equation between 2 points on 2 different streamlines. So what is missing here? Why are we not able to apply it here? And why are we able to apply it in some other situations? So there should be some condition, clear-cut concept where you should be having an idea of when to apply and when not to apply. One thing's for sure, here it is not applicable. E1 is greater than E2, you can actually get the subtraction of this. Before we get the subtraction of this and go and mark the answer in the problem, let's pause a bit here, try to clarify all our concepts and conditions for Bernoulli's equation, and then attack the problem. Okay, so I hope you're ready with that. So, okay, again, a lot of things I'll explain step by step, diagram by diagram. So concentrate carefully. So in the first of the concepts that we'll deal with, I'll try my best to depict the examples of different study flows. I already told you the example of study means things don't change with time. That means at any point you measure the velocity of the fluid, then at every other instant, the same point will have same velocity. That's the whole idea of study flow. I've given 4 examples. I've divided the page into 2 parts. The left side examples are rectilinear flows where the fluid elements go in straight lines. On the right side of the board, you have 2 more examples called as curvilinear flows where the fluid elements go in curves. And here on the right top, you could see I have taken up the example of the present problem that I've taken in this video. Let's see what are the other 3. Okay, so we'll go one by one. Let's concentrate on the left top now. Okay, so this is a very familiar flow where there is a uniform flow and also a rectilinear flow. Every point has the same speed, therefore it's a uniform V. It's already studied, remember? Now I'm saying it is also uniform. So with space also it is not varying. This type of flow we deal with is called non-viscous flow because there is no velocity gradient. We have studied this in one of our past videos. And therefore it is also irrotational flow. How do you deal with irrotational flows? Okay, at engineering levels, you have a concept called vorticity, but at JE level, a visualization can be used to depict whether or understand whether flow is rotational or irrotational. So look at this. If I have a small toothpick or a small floating wooden twig, okay, or a straight rod, which doesn't have a large weight for its own, if I place it in the flow, it will just keep going straight. You could see because of the flow, the top point and the bottom point of this particular rod move by the same speed. So you'd see that rod after some time when it comes here will not change its orientation, or can I say it is not rotating. Such a flow is called irrotational flow. Whereas if you come down and look at a familiar example of a viscous flow where there is a velocity gradient V as a function of Z, can you see? Then in that case, when you place the same twig or the toothpick that I talked about, the top point of this toothpick moves farther distance than the bottom point. And therefore, over a period of time, do you see this toothpick or a fluid element moving and also rotating? Yeah, such a flow where V of Z variation is there in rectilinear system, viscous flow is taking place, and also it's a rotational flow. So just because things are moving in straight line don't need to mean that it is irrotational. You are here, you have a situation where the flow is rectilinear, that is straight line, but also rotational. Now look at our example in the present problem, in which you have a uniform omega, and therefore you will not have any viscous forces. That means one fluid element to the next fluid element, there won't be any shear force. We have done this in one of the videos. At the next page, I will give you the link of that video in case you're new to this channel. So this type of flow where omega is uniform with respect to radial distance, that means same omega throughout, you end up always having a non-viscous flow. And but this is rotational flow. The reason is very simple. If I were to place a toothpick here, over a period of time, the toothpick always tries to point towards the center. That means you could see it is directing itself in different directions at different positions. That means it is rotating. So it's a rotational flow. So you may have in future a situation where omega is actually not uniform. You can actually find out what is the omega as a function of r, such that if I place an object which is floating and it is moving around, instead of pointing in different directions like what it did here, you may actually have the body just translating. Can you see a smiley ball here? If possible, if a non-uniform omega, one particular function you have used in which this smiley ball will actually not rotate. Can you see it is just translating, it is moving without any rotatory motion. Okay, so it's a curvilinear flow, but it is an irrotational flow. Okay, in one of our practice problems, I would request you to actually calculate what should be the value of omega as a function of r to achieve this type of curvilinear but irrotational flow. And please don't confuse between viscous and irrotational. These two are two different conditions. For viscous flow, you need shear stress and shear strain to be acting. For irrotational, you require the objects placed inside to be only, for irrotational, it should be translating, and for rotational, it should start moving by pointing in different directions. So let me, for new people, it will be slightly difficult to visualize these two diagrams. Let me slightly enlarge it in the next slide. So elaborating the two curvilinear flows, I have taken the liberty to draw them again. Okay, right on the left side, what I was pointing about, that smiley ball, I tried my best to depict it in a different diagram. Irrotational flow with object pointing same way always. Imagine, can you concentrate on this black arrow? Always, if the black arrow is pointing towards rightward direction, this type of body movement is called translatory motion. Okay, arrow is always pointing towards right. This is what happens. Let me go to the previous slide. In this fourth case at the bottom right. Okay, right, maybe someone has maintained the omega as a function of r in such a way that this can happen. Whereas to the right side of it, in a rotational flow with uniform omega, you could see that this, if you concentrate on this red arrow, like our previous example, the red arrow always points along the radial direction. That means, do you see it's rotating about itself? Therefore, this is a rotational flow. Okay, so this is the current problem that we are looking at. Okay, since it is rotational flow, you have been taught in our standard textbooks that for a rotational flow, you should be very careful. Bernoulli's theorem is not actually applicable between two different streamline points. Okay, so concept 2, and how to apply Bernoulli's equation. Okay, so here I'll give you some sources for those especially who are interested in Olympiads also. Even for JEE aspirants, knowing things at an in-depth manner will always give confidence that they have understood the topic. Okay, so follow it very carefully. Okay, so there is a book called Irving H. Shames. I have picked up the Indian edition that I have at home, third edition, in which there is a section called 7.6, and here he derives the Bernoulli's equation from the basics of thermodynamics. Okay, so it boils down in the last step to writing an equation under some special cases, which are our JEE syllabus problems, where pressure energy plus rho GH term plus half rho V square is a constant. In our problem, this term was called capital E. Okay, so can we use this equation between points 1 and 2 is the question. Okay, so first and foremost, if I take the common conditions as steady, incompressible, and non-viscous, right? Then if along with these three I have a irrotational flow, then capital E on two different streamlines will be same. Whereas for rotational flow, you can actually prove from basics and slightly higher level mathematics that the rotational flow condition ensures that on a single streamline, you can apply this equation. Single streamline, two different points you can apply, but on two different streamlines, the value of this E will be different. And that's what is happening in our present problem, which is a rotational flow. The value of E1 is not equal to E2. Okay, on the first streamline, all points will have same E called E1, and the second streamline, all points will have different value of E called E2. That's what is happening. So for the proof, go to this section, try it out. It is a pretty straightforward one. You need to just know the idea of gradient in this context. Whereas for JEE aspirants who are not interested in the proof, it's a thumb rule that H.C. Verma sir teaches us in his book, our NCERT textbook teaches, by asking us to remember that study incompressible, non-viscous and irrotational flow. All these four conditions ensure that you can apply not just at 2 points on single streamline, but you can apply it between 2 points of two different streamlines. So this rotational was a very important concept there. Okay, so let's move forward with the concept 2 that we have accomplished. Complete our problem now. So we have already derived the value of P1 minus P2, the outside minus inside pressure as this, using the integration. And we know that in this problem, because the gravity is not involved, it's a horizontal diagram, the value of E comes out to be P plus half rho V square. Since V is more and P is more, the value of V1, that is outside one, is B omega, and V2, the inside one, is A omega. You should be able to subtract E1 and E2. Therefore, will be P1 minus P2, this term, 1. And V1 minus V2 will also ensure that you get a B square minus A square by 2. So 2 halves make it this term. So the value of the fluid element's energies outwards is much larger than the values of the fluid energies inside, and they're not equal to each other. So Bernoulli's equation here is not applicable as it's a rotational flow. Okay, right? Let me correct the spelling of rotational here. Yeah. Okay, so let me mark the option now, and then we'll move on to the practice problems and some of the video sources I wanted to give you to get a feel of this rotational and irrotational flow. So just stay there. Okay, right. So P1 minus P2 is half that thing, and E1 minus E2, this. So just in case you have marked option C or B, then you maybe were misguided in concept, and I hope the video of resolved series was helpful in clarifying that misconception. Okay, so let's move forward. We have done with this. That's a bonus idea now. Some students argue, how can I modify the Bernoulli's theorem, right, by sitting in a rotating frame? The previous idea was from rest frame or absolute rest frame. So you can actually fix yourself. Can you see in the diagram? Imagine you are the person who is affixed to the rotating frame. Your head is also rotating with the same omega as the omega of the liquid. Then what do you see as you turn? The liquid also turns along with you, and you'd see the same fluid element in front of you. So in this particular frame, the liquid looks frozen or is at rest. And we can use Bernoulli's equation in this rotating frame, provided we use a pseudo potential energy term. Because this fellow sees a centrifugal, radially outward centrifugal force, which gives rise to a potential energy term, which was absent. Remember, this is like a pseudo gravity that is radially outwards. So I don't want to waste the time of this video exploring that, because we have solved the problem using rest frame. But for those who are interested, they can explore this idea of pseudo potential energy in the PDF that I have shared in the description below. Open that PDF. It is an MIT question and very basic JEE advanced level, and go to the section 2.3 in that. There are 3 or 4 pages in that PDF. You can go to that page and section 2.3, just take it out, and the same idea will give rise to the same answer that we solved in the rest frame. Okay, so I hope this is also out of our way. Now, in order to get a feel of what I was saying in static pictures, it won't be clear. Before we move on to the practice problems, watch this wonderful old video. Okay, I have given the link of this video in the description, but since this is very old, it keeps getting deleted from different channels. Okay, so just in case you are watching this and by this point, this link that I have put in the description is deleted, you can also search for in the YouTube search engine, the Vorticity part 1 by a person, Shapiro. He's made beautiful videos in 1960s. Okay, this is a very old video. You could see it's a low quality video with a high quality content. Okay, so straight to the point, great descriptions and great visuals. Okay, so if you're concentrating, and put the subtitles, and then you can enjoy. So you'll get a visual feel of what I actually said in the previous slides about the rotational flow. If I put a toothpick, this is a toothpick that is almost put and it's turning, it always points in the radial direction. He tells you that it is rotational flow. And also the irrotational one that I spoke of is also there. You can watch the first 10 minutes. Okay, so in order to get a feel, if you are a Olympiad aspirant and want to know Vorticity, you can go ahead and watch the entire 20 minutes. Okay, so first 10 minutes is enough for the JEE aspirants. Okay, now let's move on to the practice problems. There are 7 of them, so please keep a note of them and pause the video, have a try, and in the comment section below, as is the case every time, comment the answer with the timestamp of this particular video so that I can reply whether it's correct or not. And I'll answer these in the PHYSICSSIRJEE quickies. Okay, so the first question, it's a modified version of the first question of IRROTO, but there are extra options that are given that are not there in IRROTO. Okay, so, and I have underlined one condition that they have added here. So this is a common question that floats around in a lot of coaching materials. There is some small discrepancy here, which I'll explain in the PHYSICSSIRJEE quickies solution. Okay, so I've underlined. So for the party of the question, take this information, whereas attempt this question again, right, for more than one, if the underlined part is omitted. So someone, let's say, doesn't give you this information that the fluid elements have same net energy density, then what will be your response? It's a very interesting one. So give me an answer as part A and part B separately in the comment below. Don't forget the timestamp. Okay, let's move on to the problem number 2. So I've taken up the 4 examples, right? And in one of the things, the smiley ball was not rotating. And I said this is actually a non-uniform omega and viscous flow, but irrotational. And I asked you what is the value of omega versus r, right? So can you predict the variation of this angular speed with r using 2 methods? One is the JE idea, which I'm giving a hint, it involves the angular momentum logic. Whereas if you have already gone through that video, that old video, and also read through that Irving H. Shames 7.6 section that I already spoke of in the previous slides and understood the vorticity logic, you can also derive this using the physics Olympiad concept. So for those JEE aspirants, just stick to the method 1. Otherwise, you can go ahead with method 2. But I'll give answer with both the methods in the PHYSICSSIRJEE quickies, and you can comment the answer below with the timestamp so that I can respond. Okay, so for those who are looking at an understanding of how to attack questions where omega varies with r. Remember, this video had omega as a uniform value, but omega varies with r. I've already done 2 nice videos, one in the resolved 7th video, right? And I solved a question comprehensively of 1.333 of IRROTO. Also derived this expression that he gave in the question in a proper manner. Also a follow-up video for that as a challenge that he gave, where the liquid inside is kept and the cylinders outside are rotating. Okay, lot of JE concepts were covered. In case you are new to this channel, it is a must that you solve these 2 problems or watch these 2 videos whose links are in the description below. Don't miss them because you'll get an idea of how to attack the omega versus r situations. So this was problem 2, and then making sure that you watch these videos. Then problem number 3, a famous question that keeps getting appearing in a lot of AITS coaching materials that students generally find it difficult to, they know how to solve it, but they don't know why is it that they're writing certain equations there. Okay, so practice problem 3 and also 4, which is follow-up of this 3, will involve testing your understanding of this concept. Okay, so just read this question where liquid is on one side, there is a stopcock here, you open this valve, the liquid goes on to the other side, area of cross section is 2a, and we are assuming steady flow, treat the water as non-viscous, is asking what is the time for the levels to become equal. Okay, so these are the options given. Okay, right, so those who are solving this question, they'll get this answer, but I want to ask a conceptual question as practice problem 4. Okay, so look at this. As this liquid keeps going into this, there'll be one arbitrary instant where the liquid level has fallen and liquid level has risen to some point. Let's take a snapshot of that and ask ourselves something. So here it is, a clumsy diagram. Okay, so bear with me. I'll try to explain. So in the previous problem, at any arbitrary instant, Bernoulli's equation is valid between which of the pairs of these points? Let me explain. So original liquid level was this. Imagine this one fell to this red color level here, and water rose up till this red color level here. I marked a free surface point 1 here, free surface point 3 here, whereas 2 is just inside the valve before entering this bigger vessel. 2 is the point just inside the valve and before entering the bigger vessel. So 1 point, 2 point, and 3 points. So can you apply Bernoulli's equation like you're doing in the previous problem? You got the answer, let's suppose. I'm asking you whether you have considered applying the Bernoulli's equation between points 1 and 2, or 2 and 3, or 1 and 3, or maybe all the three. You can mark all the three, okay, right? So it's more, not more than one, or none of the points. It's not actually applicable, is what I would ask you to respond in the comment section below with the timestamp. Okay, so the red shade here in the diagram represents the arbitrary level. Okay, I'll answer this in the quickies section. Problem 5, just to cheer you up, to tell you what you have been doing in your JEE practice problems is correct. Okay, so this is a very straightforward one. Okay, so when there is a uniform flow, that means every speed point is u, then between two different streamlines, how do you operate and calculate the PB minus PA if this is vertical direction? Acceleration due to gravity, let me mark it so that there's no confusion. So acceleration due to gravity is in this direction and the value of that is G. Okay, I think this is very straight one right now, but now you know why you can apply the Bernoulli's equation between two different points on a streamline. Okay, so sixth one, another interesting one. You have an orifice here where the liquid starts jumping out, okay, fluxing out, and you draw streamlines for the liquid. And at one horizontal line, if I have point 1 and 2 on two different streamlines, remember 1 and 2 at the same horizontal level, but two different streamlines. Understanding the concept that I have taught till now in the video, try to comment which of these options are the most appropriate. And while commenting, I want extra thing here. What are the assumptions that you have considered while picking up the options? Okay, so this would be very interesting, maybe slightly controversial, but we'll try to dissect this in the PHYSICSSIRJEE quickies as soon as possible in the coming week. Okay, right. Last one, right? This should also interest you a lot. It's about streamlines and the momentum carried in a two-dimensional flow. So question is in front of you. I don't want to spoil your experience by reading it now. Pause the video, read it properly, and comment your answer among the 4 options with the timestamp below. I'll respond. Okay, so these are the 7 practice problems I would request you to attempt to ensure that Streamlines concept and Bernoulli's theorem application is very much resolved for JEE advanced level. Okay, so there are many more series parallelly running in this channel. Please do check out the links of the playlist in the description below. If you're new, please ensure you try to like, share, and subscribe. Hit the notification bell icon so that you can get the regular updates, and keep yourself updated because there are 200 plus videos in this channel. So if you're new, try covering as many as possible before your examinations. Okay, so thanks for staying this long. I loved bringing this particular concept by dissecting this. I hope you have done the same. And with the same kind of enthusiasm, let's meet in the next video.